Okay, let's start. So what we studied, we are in chapter 14, right? Am I audible?
Yes.
So chapter 14, what we covered. So we started with what are the basic building block, right, of electronic circuits. The olden days it was vacuum tubes. Now it is solid state devices, is semiconductor, right? Solid state semiconductor. It's the new building blocks. Using this only we are making the electronic circuits or electronic devices. Okay. So this is example vacuum diode, and this is junction diode and bipolar junction BJT are some examples for what semiconductor devices that we discussed. Then classification of solids, right? So what are the different classification of solids? We know that it's metal, semiconductor, and insulator. So the resistivity and what is the conductivity, so that we studied. And classification of semiconductors on the basis of chemical composition, right? So elemental and compound. So what are the examples for elemental semiconductors? What are the examples of for elemental semiconductors?
Silicon and Germany.
Silicon and germanium. And for compound, we have inorganic, inorganic, organic, and organic polymers, right? So mostly used was elemental and compound inorganic semiconductors. That is, silicon germanium is elemental, and cadmium selenide, gallium arsenide, indium phosphorus, I think, yeah, etc. are the compound word semiconductors. Now, the important part under this chapter is energy bands. So, what we studied under this energy, so what is the difference here and here? Here it is energy levels, right? So, here only one atom of sodium, but here we have,
Sir,
yes.
screen share అయిందంట.
Okay. Now you can see, right? Sorry, I forgot to share it. So, these are the energy levels, okay, and these are the energy bands, right? So what is the difference? In here only one atom, there will be multiple atoms. So when the multiple atoms comes, there are energy band. What is the cause? We discussed in the last class. What is the cause? What is the cause? Why we have energy band when there are multiple atoms? Who knows the answer?
The atom interact.
Yes, there will be interaction between multiple atoms, right? So that's why even though all the electrons, like even though in the same orbit, okay, but due to these interactions, the same, that will be the valence electrons. So each valence electrons in each atom will have different energy levels. So that's why we cannot give a single energy level. There will be a band. So that band formation of energy is coming. Then we discuss with a silicon crystal, right? So when the distance decreases, so what happens? Finally there will be two bands. One is valence band, another one is the conduction band. So what is valence band and what is conduction band? That is the ultimate thing you have to remember. What is valence band and what is conduction band? So in normal silicon atom, if you took, we have how many valence electrons in the outermost shell? How many electrons we have for silicon and germanium? We have 4 number of electrons, right? So in normal condition they will be in the valence band, right? So valence band is the highest energy band filled with valence electrons, okay. But when the thermal energy, when these electrons get some kind of thermal energy, what happens? This will move to another level, So that we'll call it as conduction band, and that will cause the current, electric current. So the lowest unfilled energy band next to the valence band. So from the valence band, if the electrons get higher energy than the valence band energy, it will move to where another band. So that band we will call it as conduction band. Okay. So those electrons or charges which are in the conduction band, which reaches to the conduction band, so that transition causes for the electric current. So that we discussed about. So this you should understand what is valence band and what is conduction band. So the concept you have to understand, because throughout the section we will be dealing this valence band and conduction band. And the energy gap between these two, we'll call it as forbidden energy gap. So which having the lowest forbidden energy gap, metal, semiconductor, or insulator? Which solid device having the lowest forbidden energy gap? Hmm?
Con-
Hmm?
Conductor.
Conductors, that is metals, right? Metals conductor. So conductors will have the lowest energy gap. So easily it can go to the conduction band and cause what? Electric current, right? So that's why metals normally shows good conductivity. Okay. And the highest forbidden energy gap is for what? For insulate. Now we're coming to the core of this chapter. So we classifying the semiconductor on the source basis of the source and nature of charge carriers. Which charge carriers, whether the electrons or the holes, creating or causes for the current through that semiconductor. Based on that, we classified the semiconductor into intrinsic and extrinsic. Previous classification was based on the chemical composition, right? Elemental and compound. Here it is based on the nature of charge carriers. We classified into intrinsic and extrinsic semiconductor. So extrinsic, again we have classified into N type and P type semiconductor. So what is intrinsic and what is extrinsic? That you have to understand. So intrinsic semiconductor means if I'm taking a silicon, if I'm taking a germanium pure, there is no impurity. Only silicon atoms will be there. Only if I take a silicon crystal, so this will have only silicon atoms. If I take a germanium crystal, so it will have only germanium crystal. So that is, we will call it as a pure semiconductor, right? But it's not its ideal condition, but there will be some amount of impurity. That impurity will be less than 1 part per million, like a 1 part for 10 power 10. If you take 10 power 10 parts, if you divided the total atoms of germanium, so for example, if I'm taking a silicon or germanium crystal and it is having approximately what you call 10 to the power 300 approximately, I'm telling, okay, 10 to the power 300 amount of what? Silicon atom. So in that, if I'm divided that 10 to the power 300 into a group of 10 to the power 10, 10 to the power 10, multiple groups which is having 10 to the power 10 atoms of what? Silicon. Okay. So in that only one impurity will be there. So that's its meaning. Like in pure semiconductor with impurity less than 1 part in 10 to the power. So what it is mean? If I take a crystal, silicon crystal, so if I'm, let it be, it is having silicon atom, how many? 10 to the power 300 how silicon atoms here, like this, n number of, okay, all of silicon atoms. So how many? 10 to the power 300 silicon atom. Now I am grouping the silicon atom a group of 10 to the power 100, 10 to the power 10. This is one group, this is another group, This is another group. So each group will be have how many silicon atom? 10 to the power 10 silicon atom. Okay. This group will have 10 to the power 10 silicon atom. This group will have 10 to the power silicon atom. This group will have 10 to the power 10 silicon atom. So I am grouping this total silicon atom. How many total silicon atoms are there? 10 to the power 300. I am grouping each group in such a way that each group will have 10 to the power 10 silicon atom. Okay. So if I group like that, one group, each group will have only one impurity of other metals. Let it be arsenic, let it be boron, any other metal. Yes, that kind of purity is there. So that type of semiconductor we will call it as intrinsic semiconductor. Clear? Clear? So no. Yes or no? Yes or no? No.
Yes.
Clear? What is the purity? 10 to the, what is the meaning of the pure semiconductor with impurity less than 1 part in 10 to the power 10? Somebody saying like that. Can you able to visualize what it meaning? If I'm taking the total atoms, I'm grouping in each in such a way that each group will have 10 to the power 10 what silicon atom. So in that group only one impurity will be there. So that is the meaning of this statement. Very, very important statement. You should understand. If it is not clear, please let me know. We have to do problems based on this. So hope it is clear, right? So let me move. Now, in the case of intrinsic, this is first property. Second property is the charge carriers are due to the intrinsic property. That means inbuilt property of the material and also due to thermal excitation. To the intrinsic or inbuilt quality of that material, and also if some thermal excitation or thermal energy increases, due to that this conduction happens. Okay, and also the third property of intrinsic is the number of free electrons will be equal to the number of free holes. So these three properties are the case of intrinsic. So it is pure semiconductor in such a way that impurity will be in one if I'm dividing into 10 to the power 10 group, in a group with having each group having 10 to the power 10 atoms. So in that group will have only one impurity, that is intrinsic. And another important part is the number of free electrons will be equal to number of free holes. Okay. Now we will come to the extrinsic. So here extrinsic semiconductors are more important because these semiconductors will be used in most of the electronic devices, either N-type or P-type. What is N-type and what is P-type? How we can make this N-type and P-type semiconductor, we will see in the coming slides. So here Ne is equal to that already told. So here the semiconductor obtained by adding impurities. So here intrinsic it is pure semiconductor. We are not adding any kind of impurities in the case of intrinsic. But in the kind of extrinsic semiconductor, we are adding some impurities externally. So we will be adding some tri or pentavalent impurities. Can you tell some trivalent impurity name?
Boron.
Boron, aluminum, right? So it's a trivalent impurity. And pentavalent impurity, can you tell some example for pentavalent impurity?
Arsenic.
Arsenic, right? So these are two examples for trivalent and pentavalent. So using by adding these impurities, we can make extrinsic semiconductor. So if I am adding trivalent impurity to a pure semiconductor, silicon or germanium, what we will get? We will get p-type semiconductor. If I'm adding pentavalent impurities to a pure silicon crystal, we will get n-type semiconductor, n-type extrinsic semiconductor. How we will get? We are going to see. We are going to see how we can create or construct an n-type and p-type extrinsic semiconductor. So from this slide, so you have to understand how we can classify a semiconductor intrinsic and extrinsic. What is intrinsic and what is extrinsic? And what is n-type and what is p-type? How we can, if I'm adding impurity, what type of impurity I have to add to make n-type extrinsic semiconductor, and to make p-type semiconductor, extrinsic semiconductor, what type of impurity I have to add. These points you have to should be clear. Okay, so let me ask question then. So what is the difference between intrinsic and extrinsic semiconductor? Sri Lashmi, what is the main difference when you hear about that is intrinsic, this is extrinsic? So what you will understand?
Intrinsic semiconductors are semiconductors which have a very less impurity, like less than uh, 1 part of 10 to the power of 10.
Okay, and what about, yeah,
Semiconductors with like which are obtained by adding impurities.
fine. So we will be adding externally impurities. That's why we get, that's why the name extrinsic. Okay, so for getting n-type semiconductor, what type of impurities we have to add, Aditya? Aditya, Aditya, Aditya.
സാർ എന്നെയാണ് വിളിച്ചത്? ഓക്കെ.
എത്ര നേരം വിളിക്കണു?
അല്ല, ഞാൻ വേറെ എന്തോ
ഇവിടെ ഉണ്ടായിരുന്നില്ല എന്ന് എനിക്ക് മനസ്സിലായി, എവിടെയോ പോയി. അപ്പോ
ഇല്ല, പോയിട്ടില്ല.
ആ,
ഇവിടെ തന്നെ
എന്നാ പറഞ്ഞേ, എന്താ ചോദ്യം?
വേറെ എന്തോ.
വീഡിയോ ഓൺ ചെയ്യാതെ പറ്റില്ല കേട്ടോ, വീഡിയോ ഓൺ ചെയ്തേ പറ്റൂ. ക്യാപ്പ് വെച്ചാൽ മതി. ക്യാപ്പ് വെച്ചിട്ട് ഇന്നിപ്പോ കുഴപ്പമില്ല, നെക്സ്റ്റ് ക്ലാസ് മുതൽ ക്യാപ്പ് വെച്ചിട്ട് വീഡിയോ ഓൺ ചെയ്താൽ മതി. പറയൂ. How we can make, what type of impurity I have to add to make n-type semiconductor, n-type extrinsic semiconductor? കേക്കാവോ? ക്വസ്റ്റ്യൻ കേക്കാവോ?
സാർ എന്താ, ഹൗ വി ക്യാൻ മേക്ക്
n-type extrinsic semiconductor? എനിക്കറിയാം, വീഡിയോ ഓഫ് ചെയ്ത് കഴിഞ്ഞാൽ നിങ്ങളെല്ലാം നിങ്ങൾ ഇഷ്ടത്തിന് എവിടെയെങ്കിലൊക്കെ പോകും. അനുഗ്രഹ, how we can make n-type semiconductor?
ക്ലിയർ ആയിട്ട് കേട്ടില്ല.
പറഞ്ഞതൊന്നും ഞാൻ കേട്ടില്ല കേട്ടോ. അറിയാവോ? എന്നാ പറയൂ.
മറ്റേ എന്താ ഇൻട്രിൻസിക് സെമി അല്ല,
How we can make n-type extrinsic semiconductor? What type of impurity have to add?
നെഗറ്റീവ് ചാർജ് ഓഫ് ഇലക്ട്രോൺ.
നെഗറ്റീവ് ചാർജ് എന്നുള്ള കാര്യമേ ഞാൻ പറഞ്ഞിട്ടില്ല ക്ലാസ്സിൽ. ഞാൻ എന്തിനാ ഇവിടെ പ്രസംഗിക്കണേ?
അല്ല,
വീഡിയോ ഓൺ ചെയ്യാൻ പറഞ്ഞു കഴിഞ്ഞാൽ ഓൺ ചെയ്യില്ല. അത്ര പോട്ടെ, ഓൺ ചെയ്യണ്ട. ക്ലാസ് ശ്രദ്ധിക്കുന്നുണ്ടെങ്കിൽ ഞാൻ പറയില്ല ഓൺ ചെയ്യാൻ. പറയൂ. ഞാൻ ആകെ ഈ ചെറിയൊരു കോൺസെപ്റ്റ് മാത്രമാണ് ഈ അരമണിക്കൂറായിട്ട് പറഞ്ഞുകൊണ്ടിരിക്കുന്നത്. അറിയോ? ആൻസർ അറിയോ? ആദിത്യ അറിയോ? ആദിത്യ
ഇല്ല സർ.
കേട്ടില്ല.
ഇല്ല.
അറിയില്ല. ഓക്കെ, അനുഗ്രഹ പറയൂ.
By adding pentavalent impurities.
For getting, yes, for getting n-type semiconductor, n-type extrinsic semiconductor, we have to add pentavalent what? Impurity. And for getting p-type semiconductor, what type of impurities you have to add, Niranjana?
Trivalent impurities.
Trivalent impurities. Okay, now just see how an intrinsic semiconductor looks like. So I'm taking a silicon or germanium crystal. Okay, so what is this for? So this 4 is showing the valence electrons of a silicon or germanium. So this is a silicon or germanium crystal which is having n number of atoms. Okay, so these are different atoms, but I'm showing only the valence electrons of each atom. So how many valence electrons for silicon and germanium? We have 4 number of valence electrons. Okay.
Sir,
Yes.
sir,
Okay. Listen.
Tuesday.
Switch on the camera and listen. Listen. Okay. See, so this is a crystal of silicon or germanium and it is at very low temperature. Okay, so this I am showing its 4 is means it is the what? Valence electrons. This is valence electrons. So this is one silicon atom, this is another silicon, another silicon, another silicon. So what is this? This is the covalent bond. Covalent bond between the adjacent crystal atom. So if I am taking a center crystal atom, there will be 4 crystal atoms surrounding it, which makes a covalent bond. Okay, covalent bond. So this electrons shared from this silicon atom and this electron is from this silicon atom. So using that covalent bond, it's okay. These are different 4 pair of covalent bonds. And this dots we call it as electron. And this plus 4 we are indicating it is the what? The valence electrons of silicon. So this condition is at normal, it's very low temperature. So when the temperature increases or the thermal generation of electrons on holes happens. So when I'm increasing the temperature from room temperature to somewhat higher temperature, so what happens? See, so this there are electrons here, right? So this electron will get excited, will get a higher number of energy and it will move to conduction band. Here all are in valence band, right? All are under valence band. All, even though it is under covalent bond, so they are tightly coupled, right? So you cannot move in normal temperature. So this is all are valence band electrons. So but here when the thermal excitation happens, this single electrons will move out of this covalent band, creating a hole here. We will call this is a hole. So this is the absence of electron. From where this electron moves out, so there a hole will be created, electron vacancy. Okay, then what happens? Another electron from here, nearby electron, will move to this what? Hole. So this I am taking it as site 1 and this I am taking it as site 2. This site 1, first electron is excited and moved to the what? Conduction band here. Then hole is generated here. To this hole from the adjacent covalent band, here it is moving and it will fill this hole. So what happens? A new hole will create here. So what happened? Hole is creating. There is a movement of hole, right? So there is a conduction or movement of hole. So initially it was here. Now hole will be moved to here. So electrons will be moved in opposite direction of. Suppose electron is moved in the upward, holes are moving in the downward. Both will in the opposite direction. So it will create a what? Electron current and also a hole current. Clear? Is it clear?
Yes.
Okay. Now, see, this first case, smooth out this electron, hole is created. From the side 2, this electron is moved and filled to the side 1 hole. So what happens? The whole movement is happening. So motion of a hole. So the total current that is created in an intrinsic semiconductor is equal to what? I is equal to I plus IH. That is, the electron current will be in one direction. In the opposite direction, there will be a hole current. So, IE is the electron current, IH is the hole current. Both magnitude is same, but both are in opposite direction. Both will be equal, right? IE will be equal to IH in the case of intrinsic semiconductor, because number of holes and number of electrons generator will be equal. That is very important point in the case of intrinsic semiconductor. Number of electrons generated and number of holes generated will be equal, and the total current in the case of intrinsic semiconductor I is equal to electron current plus hole. Clear? So here let me summarize what you have to understand. The first figure is the normal temperature. When the temperature increases, what happens? Free electrons get generated. The hole will be generated. So from the nearby atom, the hole will be moved to this. So there will be electron conduction and hole conduction. That means current due to electron and current due to hole. Both magnitude will be equal. The total current in the intrinsic semiconductor is equal to IE plus IH. Electron current plus hole. Clear? Ranchana, Aditya,
Yes, sir.
Aditya,
Yes, sir.
clear? Okay. See, electron current and hole current. E. Now, can you imagine how will be the energy band diagram? Previously, we have seen energy band diagram, right? How it will be here, right? So here, this is valence band. This will be what? Conduction band. In the case of intrinsic semiconductor at very low temperature, how will be this energy band diagram? Where will be more electrons and where will be, like, how it will be? This valence band will have what? Let me show that. See, this figure, the first figure is the temperature at 0 Kelvin. 0 Kelvin means very low temperature. We have like insulator. So this is valence band and this is conduction band. The first figure in the previous, is there any kind of like there is no free electron, right? Here there is no free electron. All the electrons are in the valence band. In conduction band, there is no free electron, right? In this figure, undo free electron undo. But first figure, covalent bond. So all the electrons are available in the valence band. So let me move to the next slide. See, these black dots are electrons. So at the low temperature, at the very low temperature, all the electrons will be available in the what? valence band. In the conduction band, there is no electrons. There is no electrons. Now come to the second picture. What happens here? Can you think? When temperature increases, what happens? When temperature increases, so this electron will get energy and it will move to the conduction band. Right? This electron will get energy conduction. So some of the electrons from this silicon atom or germanium crystal, not atom, silicon crystal or germanium crystal, which is having n number of atoms. So some of the electrons which is thermally excited will move to the conduction band and it cause what? Cause conduction, electric current. Now you have to note one more point here. So the number of holes generated is equal to number of electrons generated, right? So the number of electrons generated through the thermal excitation is equal to number of holes generated through thermal excitation. This point also you have to remember. So are you able to differentiate these two figures? This is at low temperature and this is when the temperature is greater than 0 Kelvin. Any doubt? Those what I explained in the previous with 3 different diagrams of crystals. Here I am representing that with the energy band diagram. Energy band diagram. Is it clear why this is blank? Why there is some electrons coming here when temperature increases, and why this number of holes is equal to number of electrons. These 3 points you have to understand. And this is at temperature low and this is at temperature is greater than 0. These 4 points you have to understand. Is it clear? Clear or not?
Yes, sir.
Okay. So you can make short notes if you want. I will be sharing the notes and written notes PDF I will be sharing. I think already shared. So I will share updated one. Any doubts? So how these electrons are generated? This is intrinsic. This is the energy band diagram of intrinsic semiconductor. So how these electrons in the conduction band is generated here? Renju. How these electrons coming or generated or it is moving to the conduction band. Here it is, there is no electrons in the conduction band, but here in the conduction band electrons, 4 electrons are coming. How it happened?
Temperature increase.
Yes.
Electron get
Temperature.
excited.
Yes. So in the case of extrinsic or intrinsic semiconductor, all the charge carriers are created only because of what? Thermal excitation. Okay, only because of thermal excitation. And the number of holes generated is equal to number of electrons generated. Okay, so that's all about the intrinsic semiconductor. Let me ask one question. So this carbon, okay, this is a question in your textbook. So we discussed about intrinsic. Okay, now we are going to extrinsic semiconductor explanation. Before that, you have to understand. So just we have to like explain one question. We have carbon, silicon, and germanium have same lattice structure. So lattice structure means what? The minimum distance between the atoms are almost equal. Okay, lattice distance is nothing but the minimum distance between, what is lattice distance? What is lattice distance? So this distance A, right? This is the minimum distance. After that, we cannot reduce the distance between the atoms. So that is lattice distance. So at a lattice distance, all the carbon, silicon, and germanium will have same lattice distance. Now, what is the atomic number? What is atomic number? Or how many valence electrons in the case of silicon and germanium? How many valence electron in the case of silicon and germanium? 4, right? For carbon also, how many valence electron? What is the atomic number of carbon? 6 or 4? 6, right? Okay. So how many valence electron for carbon? 4. Silicon also 4. Germanium also 4. But carbon is an insulator. But silicon and germanium are semiconductors. Pure silicon and pure germanium are intrinsic semiconductor. Why? Can you think? Without reading that solution, can you think your own? Just think about the atomic structure. How many orbits? Where the electrons are positioned in the case of carbon when compared to silicon and germanium?
Carbon do not have vacant d orbitals for electrons to get excited.
Mm, 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 mm. That's not correct answer. Think. Where the electrons, how many orbits are there? In the case of 2, 4, right? 2, 4. So valence electrons are in the second orbit in the case of carbon. But in the case of silicon and germanium, what is the atomic number? 14, right? 14, right? Yes or no? What is the atomic number, Advait, for silicon and germanium? Advait?
അറിഞ്ഞൂടാ സാർ യെസ് സാർ അറിഞ്ഞൂടാ
അറിഞ്ഞൂടാ. Aditya, what is the atomic number of silicon and germanium?
4. Oh, sorry. Valence electron.
Valence electron is 4. Atomic number?
Silicon. മറ്റേ 14.
14, right? So 2, 8, 4, right? So the valence electron are coming in the third orbit in the case of silicon and germanium. But in the case of carbon, the valence electrons are coming in the second orbit. So in the case of carbon, the electrons are more attracted towards, the force towards the nucleus is more, right? Because the distance is very less in the case of carbon. But in the case of silicon and germanium, the distance, since the valence electrons are in the third orbit, the force towards the nucleus is very less when compared to carbon. So in the case of silicon and germanium, they can easily excited. The valence electron can be easily excited, but in the case of carbon, it is not that much easy. That's why carbon is an insulator. Silicon and germanium are what? Semiconductors. Clear? Okay.
Yes.
Okay. The second, third, and fourth orbit. So in the germanium, what is the atomic number? It's not 14, right? Silicon is the 14. I'm very weak on chemistry. Silicon, it is 14, right? Germanium, what is the atomic number? Nobody knows.
32.
30? 32. So it will come in the fourth orbit, right? So carbon is like insulator, semiconductor, germanium are silicon and germanium are semiconductor, but in the case of germanium, it is very easy to excite the electrons when compared to silicon also, because in the case of germanium, that valence electrons are in the fourth orbit. Okay, okay, clear? Any doubt? Why carbon is an insulator, even though it's having 4 valence electrons? Is it clear, Advait? Is it clear?
Yes, sir. Korchokke. Yes.
Now we will be moving to extrinsic semiconductor. Okay, till now what we discussed is intrinsic semiconductor, that is pure semiconductor. Now we are moving to extrinsic semiconductor. So what are the different semiconductors, different types available under extrinsic semiconductor? P type and N type, or N type and P type, right? See, now we will take the same crystal. Okay, so I'm taking a crystal. Okay, here also initially let it be 4. Let it be 4. Let it be 4 initially. Okay, so what I am doing is I will be adding a pentavalent impurity. That means pentavalent atom, that is arsenic. Okay, that impurity addition will be very like negligible. It's not like number of atoms and number of impurity when compared, it will be impurity amount will be very less. So what happens, I'm taking one impurity atom at the center, around that the main silicon or germanium atoms. So this 4 is showing in this what, germanium or silicon atom. So this is the impurity atom. Since this is having 5 electrons, 1 2 3 4 5, right? 5 valence electrons. This impurity is a pentavalent. This is having 5 electrons. The 4 electrons will make covalent bond. So this is first will make a covalent bond. This is another one, covalent bond. This is another, third one, fourth one. So all the 4 electrons of this impurity arsenic will make covalent bond with the nearby silicon atom. So one electron is left. It is free. It is free. There is no covalent bond for the 5th electrons of that impurity. So this can easily move to the conduction band. Yes or no? These electrons are free, right? So this can easily move to the conduction band. But in the case of P type, same way what I will add? I will add a trivalent atom or impurity, that is boron. Example is boron. So it's having how many valence electron? Boron, 3 valence electrons, that it is showing here. Okay. Okay. Now what happens? This impurity have how many electrons? How many electrons? This I am adding boron. This is N type we discussed. Now we are coming to P type. I am adding a boron atom to a silicon crystal. So what happens? How many electrons for boron? Valence electron. How many? Aditya, how many valence electron for this impurity? Boron.
Um, wait. മൂന്ന്
3, right? So this impurity is added to the P type for this silicon. So this is having 3 electrons. So how many covalent bond it can make with this nearby atom? These are silicon atoms. These are silicon atoms. So these 3 electrons it is having this impurity. This first electron will make a covalent bond with this. The second one will make a covalent bond with this, and the third one will make a covalent bond with this. But in the case of fourth, there is a deficiency of electron. There is no electron available with this impurity to make a covalent bond with this atom. So there is an absence of electron. The absence of electron, what we will call? We will call it as what? Hole. Right? Here, when we add pentavalent, it's having 5 electrons. 4 electrons makes covalent bond with the nearby silicon atom. 1 electron extra. So that's why it's called it as N type. N means somewhat negative. We can call it as negative. So since electrons have negative charge, we can call it as N type is negative type. So since electrons are coming is extra here. Electrons, when I added pentavalent impurity to a silicon or germanium crystal, we got electrons as excess. So this type we will call it N type. But when we add trivalent impurity, what happened? There is a deficiency of electron to make a covalent bond. So this is a what? Hole. It's a positive charge. So that's why we call it as a p-type semiconductor. So this way we are getting N-type semiconductor, and this way we are getting, when adding trivalent, we will be getting p-type semiconductor. Clear? Clear? How we are getting N-type? How we are getting p-type? If we are not speaking, what I will understand, like whether it is clear, whether it is not clear, should interact.
Yes, sir.
വേറെ പറഞ്ഞേ
സർ ഞാൻ
ആണോ? ആ, ഓക്കെ.
സാർ നമ്മൾ പറയുന്നത് കേൾക്കുന്നില്ലേ? 2-3 വട്ടം യെസ് പറഞ്ഞു.
ഞാൻ കേട്ടില്ലല്ലോ. എന്താണോ, നിങ്ങൾ മ്യൂട്ട് ചെയ്തിട്ടാണ് പറയുന്നത് തോന്നുന്നു.
അല്ല
ഓക്കെ
അല്ല
അല്ലേ? ഓക്കെ, ഞാൻ കേട്ടില്ല.
സാറ് നേരത്തെ പറഞ്ഞൊന്നും കേൾക്കണ്ടായിരുന്നില്ല, ഇടയ്ക്ക് വോയിസ് കട്ടാവുണ്ട്.
എല്ലാരും കേട്ടോ വോയിസ്?
ഇടയ്ക്ക്
ഇപ്പൊ ക്ലിയർ അല്ലേ? ഓക്കെ, ഇത് ക്ലിയർ ആയോ? അത് പറയൂ. എങ്ങനെയാണ്, ഹൗ വി ആർ മേക്കിംഗ് എൻ ടൈപ്പ്? So this structure also you have to remember. So when they ask the question how we can make n-type semiconductor, you should able to draw this figure, and you have to show this electrons free, and here also p-type. The center you have to show the impurity, trivalent, pentavalent. So drawing is very simple, but you have to understand the concept. Clear? Okay. Now we have a schematic diagram. So normally when we come to the next level of study, we will be studying a PN junction diode. So in that case, we will be dealing with schematic diagram. We will not be drawing this figure. We will be drawing this schematic diagram. Okay. So before that, since here this pentavalent is donating an electron. Okay, this pentavalent is donating an electron. This pentavalent impurity we will call it as donor atom. Okay, we will call it as donor atom. It is donating electron. But in the case of trivalent impurity, there is a deficiency, right? It is not donating the electron. So it is ready to accept electron, right? So this we will call it as what? Acceptor. Here it is donor, pentavalent is a donor, but trivalent is a what? Acceptor. It is ready to accept electron. Now see, since we are getting electrons, right? Here free electrons. These red dots are free electrons generated in the case of extrinsic n-type semiconductor. Okay, and this plus sign, it is indicating that what? This is donor atom. Okay, so this donor atom gives electron, so it loses electron. This donor atom loses electron, that's why we are showing it is plus, and this electron is the free electrons created. Okay, this is donor atom or the donor impurity. Okay, and these are the electrons that we got by adding the impurity, pentavalent impurity. Okay, easily you can remember. Here we are getting electrons, right? So these dots will be anyway electrons, so just opposite to electron is what? Positive charge. So the donor atom will be positive. This is a schematic diagram. Okay, the same way, can you draw the p-type schematic diagram for this p-type semiconductor? What will be the difference when compared to this? What will be the difference?
Negative charge.
Negative. The core will be negative, that is acceptor. This will be negative, right? Because it is like, and instead of these electrons we will have holes, because here holes are generated, here electrons are generated, here holes are generated. Okay, so here it is acceptor, it is ready to accept. Okay, so that's it. So if it is electron, then opposite to electron it is positive core, and it is a hole, so opposite to that it is negative. That is the easy method to remember. So here it is donor, here it is acceptor. These negatives are acceptor, these are donor. Okay, so this schematic diagram you should remember. The next level we will be dealing, we will not be drawing this, so we will be dealing with this schematic diagram. So you should please feed this figure in your mind. Clear? So in the case of N-type intrinsic semiconductor, when we discussed, the important point that we discussed is the free electrons there we generated using thermal excitation. And another important point was the number of electrons generated is equal to number of holes. But in the case of extrinsic semiconductor, it is not like that. Here the number of electrons will be always greater. In the case of N-type semiconductor, the number of electrons will always greater than the number of holes, because when adding the impurity itself we got electrons, right? This is in normal temperature, but when the thermal or the temperature slightly increases, due to that also electrons will be generated, right? So already there is electrons available, right? I'm discussing about this N-type. So by adding the impurity itself, I have free electrons in normal temperature, that means very low temperature, but there is no holes at that time, right? Here there is no hole, right? I'm having only one electron, free electron. But when temperature increases, what will happen? Any of this bond will break and it will move out. So there will be two electrons and one holes, right? Right. So always the number of electrons will be greater than the number of holes in the case of N-type semiconductor. Why? Why? Why the number of electrons is always greater than number of holes in the case of N-type semiconductor? Why? 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 Pare. Renju, why the number of electrons are greater than the number of holes in the case of N-type semiconductor?
In
Hmm?
n-type pentavalent is added, so one electron would be extra.
Okay. Then when the thermally excited, what happened?
When thermally excited, one electron jump to other orbital.
So
no holes would be there in the lattice.
Okay, so what will happen? Then the number of electrons will be 2. Holes will be 1.
When the
Right now?
again get the lattice, yes.
So again temperature increases, what happens? Electrons and holes will be equal. But already there are electrons which already generated by adding the impurity. So while adding the impurity, pentavalent impurity, there is no hole generated. Only electrons. So electrons already there. Excess electrons already there. So when the temperature comes in place, some more excited electrons will be produced, but at that time equal amount of holes will be generated. But the total electrons, if you count, the electrons count will be always greater. But in the case of p-type, what will happen? When I am added impurity, holes are there. There is no electron. Right? When the temperature increases, what happens? Electrons and hole pair generated. But in the case of p-type, if I took together, what will be more? Electrons or holes? In the case of p-type, holes, right? നിരഞ്ജന മ്യൂട്ട് ചെയ്തിട്ടാണുള്ളത് അല്ലേ?
Yes, sir.
മ്യൂട്ട് ചെയ്ത് പറഞ്ഞാൽ എനിക്ക് കേൾക്കാൻ പറ്റില്ല. ഓക്കെ, നമ്മുടെ എന്താ കൂടുതലുള്ളത്? നമ്പർ ഓഫ് ഹോൾസ് ആർ ഗ്രേറ്റർ ദാൻ ദി നമ്പർ ഓഫ് ഇലക്ട്രോൺസ്, റൈറ്റ്? Number of holes. So this you have to understand why this is coming. That also you have to understand why electrons are more in the case of n-type compared to hole. Why holes are more in the case of p-type. This you have to understand. Summa by heart padikirudhu. Why this is coming? You have to ask yourself. Adana ipo explain cheyidu thannu. Okay? Think. Otherwise you will forget. Now you tell me, how will be the energy band diagram for n-type semiconductor? How will be the valence band? How will be the conduction band in the case of n-type? Both the cases I am not taking the low temperature. I am taking temperature greater than 0 Kelvin. Room temperature. Temperature കൂടുതലാണ്. See, what is this hole? So this hole and this electron are generated by thermal excitation. By thermal excitation. This hole and this electron are generated by thermal excitation. Okay? But before that, when I am creating the n-type, so I have extra electrons. All other extra electrons are created by adding the impurities. In the previous diagram, we are adding only one pentavalent, right? But when I am adding into a complete crystal, silicon crystal, I will be adding not single arsenic or single pentavalent. I will be adding multiple pentavalent, right? So each pentavalent will create what? One electron. So suppose I am adding 9 arsenic atoms as an impurity. So there will be 9 electrons already, right? So these 9 electrons are generated by the pentavalent. Already they are free in the conduction band. Okay? And this 1 electron will be by the thermal excitation. Okay? So that's why the number of holes in this valence band are less. and the number of electrons in the conduction band is higher. Clear? In the case of n-type. But in the case of p-type, so already the holes are there. When we added impurity, what happened? There is no free holes, there is no what? Free electrons. In that valence band itself there is a hole, right? So those holes are here. They are already in the valence band. But these electrons are generated by thermal excitation. Okay, let it be. These are the valence band, and these electrons and holes pair are generated by thermal excitation. That's why these holes will create some conduction due to hole, but here the complete conduction number of electrons will be greater than the number of holes. But in the case of p-type, number of holes will be more than the number of electrons. Clear? Yes or no? So the intrinsic, in the case of extrinsic, you have to remember what, how we have to construct that. Okay, how we have to construct an intrinsic semiconductor, and how we can create an extrinsic n-type and p-type semiconductor. And what are the properties of intrinsic semiconductor? What makes the conduction possible? Only the thermal excitation. In the case of the free generation or free charges are generated only because of thermal excitation in the case of what? Intrinsic. But in the case of extrinsic n-type and p-type semiconductor, how we will get the free charges? By adding the impurities as well as due to thermal excitation. And this conduction band or the energy band diagram also you have to understand, you have to study. Clear? Clear?
Yes, sir.
Okay. At this point also you have to remember, at equilibrium in any semiconductor, whether it be intrinsic semiconductor, whether it will be extrinsic semiconductor, if you multiply the number of electrons with the number of holes, will be equal to the number of electrons, square of the number of electrons of the intrinsic semiconductor. Very, very important equation you have to keep in your mind. Ne into NH is equal to Ni square. Okay, so we'll stop today. Tomorrow we will do the problem, this problem. Okay, and we will compare, have some comparison between intrinsic and extrinsic, n-type and p-type. Then we will discuss what is p-n junction diode. Very, very important topic. How we can create a p-n junction diode. Okay, so for that, what is p-type, what is n-type, how we created this should be in your mind. Otherwise, when I'm teaching this, I'll be using the what schematic diagram. This schematic diagram it should be in your mind. Then only we can understand how we can make a p-n junction diode. Okay, and how we can operate it. Okay, so those things we will discuss tomorrow. Okay, thank you. We will stop today. Thank you. Any doubt?
Thank you, sir.
Thank you, sir.
ഇല്ല
Any doubt? No. Okay.
Thank you, sir.
Thank you.